All right, this is Honors Algebra 2 Pre-Calc. We're still doing 4.1 in Algebra 2, which is about using matrices to represent data and sort of an intro to matrices. So let's talk about some properties of matrix addition. So for matrices A, B, and C, all of which have the same dimensions here, m by n, right? Addition is commutative, meaning that if you do A plus B and B plus A, you get the same matrix. So like I'm going to pick the most lazy, boring matrix I can here. We're going to do 1, 2, 3, 4 plus 5, 6, 7, 8, right? Because I'm super lazy. And I'm going to show you that that's the same as if I flip that around and do 5, 6, 7, 8 plus 1, 2, 3, 4. And it makes logical sense that it'll be the same because remember, we just add the corresponding entries. So the first entry is going to be 1 plus 5 or 5 plus 1. Either way, it's a 6. The second entry is going to be 2 plus 6 or 6 plus 2, depending on which way you do it. Either way, it's an 8. The third entry is going to be 3 plus 7 or, over here, 7 plus 3. Either way, it's a 10. And then the last entry is going to be either 4 plus 8 or 8 plus 4, but either way, it's a 12. So both sides are 6, 8, 10, and 12, right? So that's commutative, right? Addition is commutative for matrices. It is also associative, right? So associative means that if it's all addition and you're adding 3 matrices, it doesn't matter the order in which you add those matrices. So if I tack on one more matrix here, so let's tack on a matrix C. So we'll have 5, 6, 7, 8, and let's do I don't know, let's do 0, -2, -4, -6, because again, I'm super creative. So it doesn't matter if I add these two first. Now we already saw that if I add those two first, so if I put parentheses and I add these two first, I'm going to get a 6, 8, 10, and 12, right? And then I'd add it to this 0, -2, -4, -6, which means that my final answer would end up being a 6, 6, 6, 6, which I didn't intend, but hey, look what happened. All right, so that's one way to do it. Or I could have added these two first, which would have been fine. If I had gone with those two first, I'd end up with the 1, 2, 3, 4, and I would be adding it to, when I add these guys, I end up with a 5, 4, 3, 2. So 5, 4, 3, and 2. And then sure enough, when I put all those together, I end up with a matrix that is just 4 6s, right? That's fine. Or honestly, you could have just added them all across, right? 1 plus 5 plus 0 is a 6. 2 plus 6 plus -2 is a 6. 3 plus 7 minus 4 is a 6, and so on, right? So that's all we mean by associative, right? So basically, so far, it seems like matrix addition sort of functions like regular addition. Additive identity, the matrix m by n has, if the matrix m by n has a 0 in all of its entries, then it is called the identity matrix for addition, basically meaning that if you add all the zeros, right, so if you add, let's say, oh my bad, sorry guys, if you have 1, 2, 3, 4, and you add to it a matrix that is all zeros, then you get 1, 2, 3, 4 again because you were adding a bunch of zeros, right? So this is what we would call the additive identity. All right, and the additive inverse essentially says that if you add A to the opposite of A, you get that matrix that's all zeros. You get that additive identity, right? So that's all it's saying, is that there is another magic matrix that is, in fact, in this case, if our matrix A was that 1, 2, 3, 4, then the additive inverse, -A, would just be the same numbers, but with negatives, right? And if I added those two together, A plus -A would give me all zeros, okay? All right, so in example 6, we're going to talk a little bit about geometric transformations. So here's a cool thing. So this particular example I'm going to throw out there, I'm not going to make you do something like this other than maybe in the homework, and it can seem a little tedious and annoying and kind of stupid, but it's actually not. So what we're looking at here is an image of a pretty simple quadrilateral, right? So this little red shape right here that has 4 sides. But what I want to make you aware of, so you don't even think about it when you do things like stretch or shrink or change your graph in some way so that it moves. You can move it around, you can stretch and shrink it, you can sometimes make it skinny or fat, right? We don't even think about the fact that the computer technology that we have allows us to do this with images all the time, right? That whether you're using social media, whether you're using stuff for school, or just randomly using stuff on the internet, that you can manipulate images in a pretty cool way, right? when you use map images on your phone or on a computer, you can easily zoom in and zoom out and change the scale that you're looking at on a map, right? So somebody had to code that. Somebody had to understand the math behind taking an image that consists of all of these little pixels and finding a way to scale it, to make it bigger, smaller, whatever, to stretch it or shrink it vertically or horizontally, to flip it. All of this cool stuff, and all of that comes from a knowledge of coding and also a knowledge of mathematics. So when we talk about representing these points as a matrix and then performing math on them, that's the kind of thing that happens when you manipulate an image, right? And it may not specifically be matrices, but so just because something we see seems kind of tedious and like it's not necessarily going to be useful in your daily life, it might not be. That's true. It's hard to know, and it depends on what job you pick. But in some cases, when folks know how to put together their knowledge of math with different creative applications that are artistic, you end up with amazing stuff that changes the way people use technology as we have it today. So anyway, we're going to walk through some pretty straightforward examples. But again, I'm not saying that it's necessarily the most relevant thing, but I want you to see that this is a cool application. So we're asked to write A, B, C, D, the quadrilateral, as matrix P. So when we do this, what we're going to do is we're going to write the x and y coordinates, and we're going to write them for A, B, C, and D, okay? So my x coordinate for A is 3, my y coordinate, -3 rather, my y coordinate is 3. For B, I'm looking at 3, 2, and I am reading this in a way that I would not normally read a matrix, so I usually read a matrix straight across, but just for the point of filling this out, I'm reading the points 3, -2, and -2, -1. So the matrix I end up with is -3, 3, 3, -2, 3, 2, -2, -1. And that's really all they want in example 6. And we're going to talk about how to use math to make some transformations when we get to example 7. So for P6, I want you to try the same thing, right? You're going to make a matrix Q, and you're going to have, again, that X and Y, and you're going to use A, B, C, and D to fill those in. So you can pause me if you want to do it without me. So A seems to be -3, 3. B seems to be 2, 3. C seems to be 1, -3. And D seems to be -4, -3. So there's my matrix Q. All right, so when we get to E7, we're going to do a little bit of transformation. So in E7, we're asked to refer to matrix P, which I wrote up here in my terrible chicken scratch. And we're asked to graph the polygon that's represented by doing each of these mathematical operations. And in red, you'll see I did my terrible job of sketching A, B, C, D again. So let's go ahead and do 2P. So 2P is going to be double every number inside P. So -6, 6, 6, -4, 6, 4, -4, -2. So if I go ahead and put these points, my new A, and we're going to call it A prime, B prime, C prime, and D prime to indicate that they line up with A, B, and C. So this is point A. A prime is now going to be -6, which is here, and then up 6, which is here. So that's going to be my A prime, right? 6, 4 is going to be my B prime. 6, -4 is going to be my C prime. And -4, -2 is going to be my D prime. So what I end up with essentially is an image that is zoomed, I zoomed in and made this image bigger, right? It's the same image, and again, I draw like a child, so forgive me for that. But so I have my original A, B, C, D, and then I have A prime, B prime, C prime, D prime, and that's what the new image looks like, right? It looks like it's twice as big, basically. Which again is sort of like if you were to zoom in on an image, let's say on a map on your phone or something, right? Or on a picture on your phone. So let's do 1/2 P. Well, 1/2 P is going to be exactly half of all of these. So -1.5 or -3/2, it's up to you. 1.5, 1.5, -1, 1.5, 1, -1, -0.5, right? So now if I take these, this is going to be -1.5, 1.5. So that's there. And I'm not even going to squeeze in the A prime because I can't really, I'll do an arrow just to say, hey, that's A prime, right? I have a 1.5, 1. That'll be my B prime, right? I have a 1.5, -1, and I have a -1, -1/2. And what you'll see is this is half the size, right? And I didn't really label my A prime, B prime, so that's B prime there in blue and C prime and D prime, right? But you can see that it's half as big, right? And that's what happened by multiplying by half. All right, so you're going to go ahead and make a matrix here, right? So we're going to call this matrix P. It's not the same matrix that we made when we did P6 rather. So negative 3, oh hey, it's the same one. It's the P that we used before. Sorry, negative 3, 3, 3, 2, 3, negative 2, negative 2, negative 1, right? And you don't have to sketch the red one too. I mean, you certainly can if you want. They don't ask you to. So 4p is just going to be 4 times as big, which is going to be really, really big, right? So 4p, and actually we won't use red because red was the original color of the graph, right? 4p is going to be negative 12, 12, 12, negative 8, 12, 8, negative 8, negative 4, which is pretty big. I don't even know that we can go as far as 12, right? That's 4, 8. So 12 would be here. That would be a negative 12x value. So negative 12, 12 is going to be like here, right? 12 comma 8 is going to be, that's 4, 4, so that's 12. There, so it's huge, right? Like it's going to be really big. Now another way around this is to scale things by 2, but it is what it is, right? 12 comma negative 8, negative 4, negative 8 would be here, right? And then negative 8, so there's negative 8, negative 4. So it's going to look like this, which is really big relative to that original little one. If you picture what the original one looked like in red, the original one was something like this, right? So it's 4 times bigger, right? So it's like you zoom way in. And again, if I just draw my original one here, again, terrible drawing, but you get me. Now 1/4 is going to be really small, right? Like if we draw 1/4, 1/4 is going to be really small. It's going to be negative 0.75 and a 0.75, and a positive 0.75 and a 0.5, 0.75, negative 0.5, negative 0.5, and a negative 0.25. So it's going to be really, really small, right? Like hard enough to draw on this software that I probably will not successfully manage to do it. But essentially we're talking like here and 0.75 and 0.5. So here and here and here. Really tiny. But you get the gist, right? So really, really tiny. All right, cool. Moving on. That's actually going to be it for this particular video. I know it's a little bit shorter than the others. And then we'll go ahead and do a third video in this section, and that'll be it for 4.1.